Okay, Franz is our next speaker from Caltech. He's in mechanical engineering. His advisor was Tim Colonius, and he did his practicum at Lawrence Berkeley Lab in 2024. Thanks.
Thank you very much for the introduction. Today we'll be speaking with you all about simulating mass transfer with interface capturing schemes. So I'll briefly summarize in the broadest sense what I do. I do computational fluid dynamics. So essentially this just involves solving numerically on a grid the complex equations of fluid motion. Specifically, I deal with multi-component flows. These are flows with multiple fluids, phases, chemical species, et cetera. And they all sort of involve separated, all these flows have separated moving interfaces. You have breaking waves, droplets, sprays, bubbles, et cetera. So what specifically scheme do we kind of use to solve this? Well, there's two classes of methods. You have interface tracking methods where you explicitly follow a sharp interface. You keep the interface sharp. And interface capturing methods, which is what we use, where you define the materials and interfaces based on a volume fraction field. Now, due to the numerics of all of these codes, the interface gets smeared and a mixture region develops. And as one might imagine, mass transfer generally occurs where there's an interface. So it's really imperative for us to treat this mixture region consistently. So our code is multi-component flow code. It was developed in-house here at Caltech in my lab. And it's an exascale compressible multi-phase flow solver that does interface capturing, shock capturing, higher order reconstruction via Wino schemes, and benefits from MPI and GPU acceleration. As you can see from our weak scaling plots here on the right, we perform very well on large HPC systems, which means this code is really optimal for dealing with the large resolution problems that we'll end up having to attack. So these are just some examples of what we can do currently in MFC: shock droplet interactions, shock bubble cloud interactions, jet plumes, even turbulence with Taylor-Green vortices. One thing that MFC currently lacks, as you might imagine, is doing interfacial mass transfer, which is really important for the target problem that I want to be able to simulate, which is individual fuel droplet evolution and detonation waves. So what detonation waves are is where on here you have individual fuel droplets. This shock wave will come and hit the fuel droplets, they'll combust, they'll evaporate and combust, and then the energy released from this combustion process actually continues to drive the wave forward. So it's this very complex system that involves combustion, phase change, diffusion, shocks. For the purpose of this talk, I'll really focus on diffusion limited evaporation. And this whole problem has many competing timescales, but it makes it really computationally challenging because our time stepping is really determined by the shock-driven flow properties, whereas the evaporation or diffusive timescale is very long. So what ends up happening is that you have to compute many, many time steps on the order of 10 to the 7 or higher, depending on how well you resolve your droplets. So it's very computationally challenging, and we'd like to reach that. So what is diffusion-induced, diffusion-limited evaporation? So let's say we have a droplet and some gas species surrounding it. This droplet will evaporate, and that will form a saturated vapor film around the droplet. Once the saturated vapor film is there, it'll diffuse into the external gas mixture. Now, diffusion is really confined to these gas components. It really has nothing to do with the droplet at all. So that got us thinking, hey, maybe we can treat all of these gas species as a mixture, and diffusion will just change our composition within. So maybe we can save some time by doing this. So this is really one of the few math slides I have. So in original MFC, we have one volume fraction advection equation for each component in our simulation. Notice our source terms here that are related to the diffusion process is only in these gas components. So for the liquid component, it's 0. Now, conserving volume fraction, the sum of all your volume fractions has to be 1. If you sum these gas volume fraction equations, you know that your source term has to be 0. And therefore, you can kind of collapse these NG gas species into a single mixture gas volume fraction equation. And this does two things for us. One, obviously, we have fewer equations to solve. This significantly reduces our computational cost. Second, because the source term is now 0, you don't even have to really worry about what the form of the source term is. So the source term that you get, and I spent many years trying to figure out what the source term actually is, it's completely dependent on the thermodynamic assumptions you make for the diffusion process. So we don't have to worry about that at all, which is fantastic. So let's try and see if this mixture formulation works. So I'll start with a very simple 1D test case. We have nitrogen on the left, carbon dioxide on the right, separated by initially sharp interface, and each side is in pressure and temperature equilibrium, and we'll compute our diffusive fluxes via a simple binary Fickian diffusion. So what I'm plotting here is the evolution of the volume fractions. Alpha formulation is just what we get using our mixture formulation. Now for this specific test case, because we have pressure and temperature equilibrium, moles are constant, et cetera, you can actually convert our coupled PDEs into a single ODE in terms of the mass fraction. So I'll also solve that ODE and compare it to what we get in MFC. And as you can see, we have good results. So we are very confident that this mixture formulation works. So let's move on to multi-component diffusion. So if we have more than 2 gas species, you can't use binary diffusion anymore. Let's do Maxwell-Stefan. So all I did here is essentially the same test case. We just add some hydrogen, and we'll monitor the volume fraction evolution at this monitor, and you can see as well that we get good results with that. So at this point, we are very confident that for pure gas simulations, our mixture formulation is valid. But what happens when there is an immiscible phase in an immiscible component within our simulation? So for example, the liquid droplet. You do not want your gas species to mix with our liquid droplet, with our liquid droplet. So let's say in our finite volume scheme, we have 4 cells here. 2 are pure gas, 1 cell is pure liquid and gas, 1 cell is pure liquid. What should happen? We need to compute the fluxes at each of these faces. So for this left flux here, for this left face, it's surrounded by pure gas cells. You don't have to modify diffusion at all. You're free to perform full diffusion here. At this middle face, although this side is pure gas, there's a limited volume here available for the gas diffusion. So you do need to reduce the actual diffusive flux that you calculate at this phase. Even worse, at this right phase, one side is pure liquid. To keep this immiscible, no diffusion at all can be computed here. So how do we deal with this mathematically? So we'll take whatever diffusive formulation we have and we'll multiply it by a gating function g. So we decided that this gating function must satisfy a few constraints. One, as the left and right states of your face as the gas volume fraction of your left and right states goes to 1, your gating function should go to 1. It shouldn't actually change our diffusive flux at all. However, if any of them goes to 0, then this whole thing should go to 0. And obviously, G needs to be bounded by 0 and 1 for any configuration, or else you get some unphysical diffusion. So there's an infinite number of functions you can make to satisfy these constraints, and we'll just go with a simple harmonic average of your left and right states. So here I'm plotting the same exact test case here on the left, 1D binary diffusion, but added a third immiscible component here, alpha 3, and I actually smeared it initially. So what we want to happen is that the diffusion happens here as usual, as well as diffusion happens in this mixture region without really affecting the immiscible component at all. And if I run this, you can see that happens. So diffusion happens here, and your immiscible phase stays immiscible with our gas species. So with this, we're really able to, from here, to compute your diffusion limited evaporation. So I'll start with for this test case, I'll start with a cylindrical water droplet surrounded by air, and I'll initially smear the interface between the two. And note that there's no water vapor here initially at all in the simulation. So as you can see here, the water vapors, there's none. And the way our phase change module works is that we instantaneously apply phase change such that the chemical potentials here match between the liquid and the vapor. So that essentially saturates the water vapor in the mixture region. And then our diffusion module does its thing and it lets it diffuse outwards. So this, in essence, is our diffusion limited evaporation. The net rate of mass transfer here at the boundary is completely limited by how fast your vapor can diffuse outwards. The last few things I'll talk about is making sure that this diffusion module is valid with our shock capturing techniques. So here I'm plotting what the real microstructure of an arbitrary shock will look like. It will, if you resolve it deep enough and look in the microstructure, there will be smooth gradients. And of course, within these smooth gradients, diffusion, conduction, viscosity matter. However, for our shock capturing schemes, shocks are treated as sharp discontinuities. And truly, diffusion really isn't valid across this unresolved discontinuity. So for the purposes of this talk, diffusive fluxes will be suppressed if we detect that we're computing diffusion around a shock. So let's test and make sure that this all works with shock-induced flow. So here I'm plotting a cylindrical helium bubble, and it'll be shocked by air, and the shock deposits baroclinic vorticity to the material interface. This deforms the bubble and generates complex flow structures. To isolate the effect of diffusion, I'll run one case with no diffusion, one case with diffusion, and as you can see, the overall shape of the bubble is pretty much unmodified by the presence of diffusion, which is exactly what you'd want. The timescales that this flow is being simulated over is much smaller than the diffusion timescale. But the difference is that you can see these maybe small regions here. You can see that diffusion does smooth out these smaller scales, which is exactly what it's supposed to do. It's definitely not supposed to change the macroscopic flow structures of our shock-induced flows. To look at this more quantitatively, on this left plot, I track the left and right interfaces of the helium bubble over the center line, and you can see that it matches well, meaning our shock-driven flow dynamics are untouched by diffusion. However, if we look at the density over the center line, you can see that the interface is slightly smeared due to diffusion. So this is doing exactly what we want it to do. The last plot I'll show you is a Rickmeyer-Meshkov instability. A shock accelerates an initially perturbed interface, rebounds off the bottom wall, and will reshock the interface. And you can see that we do have the mushroom-like structures that is well known for the Rickmeyer-Meshkov instabilities. And then if I were to plot the perturbation growth in my MSC simulations with diffusion, we match very well with experiments. So overall, we're pretty happy with this, and it's not we don't really have much more work to do in order to work on our target problem. All that we really need to add is combustion chemistry, and I'm no combustion expert, so that might actually be a quite significant challenge. And then after that, we will be able to move towards these 3D spherical field resolve simulations as we have here with our detonation droplets. So I'd like to thank my advisors at Caltech, my group mates in our lab that also work on MSC, our collaborators at other universities, and of course, DOE CSGF and Krell Institute for their unwavering support during my PhD. You know, there were some rough times, but they never gave up on me. So with that, thank you, and I'm happy to take any questions.